Yeah, this is definitely Algebra 1 stuff. This is not really the next, I don't know, at least 2 or 3 lessons maybe is stuff that you probably already learned in Algebra 1. It's not really technically Algebra 2 stuff, but it's good review.
We're skipping grade 3, right?
I think so. Did I write that on there?
I don't know. I didn't look.
I forget. One of my classes, I don't know which class it was. One of my classes I wrote, we're going to skip a section. I forget which one it is. Did I say skip it? Okay. All right, here we go. So let's do this. I'm going to start right off with an example. All right. So this is example 1. And it says, solve the system graphically. The Algebra 1 books that I taught out of years and years ago, they would have said just solve by graphing. But it means the same thing. Solve graphically. This book says solve graphically. And I'll show you what we're talking about. So a system of equations. They don't really say that in here. Again, other books probably would have called this titled this lesson, Solving Systems of Equations by Graphing or something like that, okay? So what's a system of equation? Well, again, this is something you've probably seen in Algebra 1, right? And there's several different ways you could solve for x and y in this situation, right? We're going to first start doing it by graphing. Graphing is an okay way to do it. Sometimes, though, it's not the most, what would be a good word? It's not specific. That's the word that's popping in my head. Accurate. Sometimes it's not the most accurate way of solving for x and y. Okay, there's better ways, really, to solve for x and y. Even in my pre-calc class, we did this. We did this with matrices. Have you ever studied matrices or a matrix? We will this year, okay? So we may even solve these this year in Algebra 2 by using matrices. It's probably a lot further down the road. Again, it's my first year teaching out of this book, so I can't remember if you do or not. But do you remember seeing stuff like this? Some math books, they put this little bracket on the outside of it. Did you do this in Algebra 1? Yeah. All right. You remember solving by substitution and elimination? Yeah. We're going to eventually do that. We'll do that, I think, tomorrow. All right. But today, we're just going to do it graphically. So what we're going to do is we're going to graph both of these equations. And then how do we solve for it? How do we solve for x and y once I graph them? Where they intersect each other. Okay, it's where they intersect each other. Okay, so if I have a line like this, what do they have in common? They got that point of intersection in common, don't they? So that's what we're trying to do here. We're trying to find out what x and y works on this equation, and the same exact x and y works in the other equation. You hear what I said? All right, so you're trying to find an x and a y that doesn't just work in the first one and doesn't just work in the second one, but it works in both of them. So whatever the x is, whatever the y is, if I put it in for this and x and y, this left side is going to equal 4. If I put that x and y, that same exact x and y, in for this one and this one, it's going to come out to be 3. All right, everybody with me on that? So when my lines intersect each other, let's just do this just so you can kind of visually see what's going on. And we'll do a graph, and I'll pull out a little graph paper sheet thing to do this. And to be accurate on this, you really do need to have graph paper. All right, if you just start putting some, just put a x and a y axis and just go dash, dash, dash. If you're not very accurate, putting the dashes the correct distance apart, you're not going to be accurate getting an answer for this, okay? So on a quiz or a test, if I give you these, I will give you the graph, right? Just like I did on the last thing, all right? Just to make sure that you are accurate on this. So I'm going to make up just a couple lines just to show you. So there's one line, and let's make the other one blue. And then there's another line like this, okay? So we're going to graph these in a second. We'll do it for real. But right now, let's just say if I had two lines that intersected each other, what x and y do they both share? They share this right there. Would you agree? So on the red line, I go over this far, go up this far, right? And on the blue line, I go over the same distance to the left and the same distance up. So both of these lines would have the same what? X and y, okay? Everybody with me? So when it says solve, you're asking to find the x and to find the y. Find the point of intersection. That's what we're trying to find. Everybody good with that? That's not too hard. Let me grab a graph that I've already made. And we're not going to graph it just yet. We still got a little bit of work to do, don't we? Whoops. We got a little work to do in order to solve for x and y, and before you even graph it. You could do it a couple ways. I'm going to do two examples that are kind of like this, except one, we're going to do it by using x and y intercepts, just so we don't forget about using x and y intercepts. And then the other way is probably the way that I would prefer, and my guess is it's probably the way that you would prefer, is to do what? If I was to graph this, what would your first instinct be? Slope-intercept form, that's right. Okay, I'd put this in slope-intercept form, both of them, wouldn't you? Okay, but you could also, if you wanted to, again, this is it's kind of like the forgotten way to do it, but you could do the x and y intercepts, right, and then graph them. Let's do it that way just to remind ourselves how to do it. That's the way they do it in the book, so let's do it right now. Is it the best way? I don't know. Maybe, maybe not, but that's the way we're going to do it. So let's take that first one, that x plus 2y equals 4. And let's find the x and y intercepts. So let's do the x-intercept first. Remember how to do that? Intercept. Yeah, let y equal 0. So if that's 0, what's x? X equals what? 4. Okay? Let's find the, let's just put it right here. Let's find the y-intercept. Okay, so if I find the y-intercept, what do we do? Set the x equal to 0. So what do we have? We got 0 plus 2y equals 4. Yes? All right, and then divide both sides by 2. So what's y? Y is 2. So what's my x and y intercept? What's my ordered pair? For what? For 0. Okay, what's my y-intercept? 0 what? 2. Okay, so that's one way to graph it. All right. Again, it might have been easier just solving for y, and then you could graph it, but this is a way to do it, isn't it? It's not that hard, is it? All right, let's graph it right now. We'll do it in red. All right, so I got 4, 0. 1, 2, 3, 4. 0, it's right there. Okay, and then 0, 2 is right there. And what do I do with those? Connect them. That's it. All right, so we make it go that way. We make it go this way. And there you go. You could put arrows on it, but I don't really care about that. You with me so far? So I got one line. Whoops. I got one line. So now I got to do the other line. So what's the other line? 2x minus y equals 3. So again, let's find the x-intercept. So we set y equal to 0. So 2x equals 3. Can you do that in your head? 2x equals 3. Solve for x. 3 over 2. And what's my point then? 3 over 2 what? 0. What is 3 over 2 though? It's 1.5. Okay, so if we're going to count over on the graph, I'm not going to count over 3 over 2. I got to know what that is, and it's 1.5. All right, let's do the y-intercept. So y-intercept, we set that equal to 0. So that means what? Negative y equals 3. So what's y? So y equals what?
0.
It's negative 3. That's what I was looking for. Okay, so yeah, let's just write it in there. So it's 0 what? Negative 3. Everybody see that? All right, so let's plot them. Let's do this in blue. So 1.5, right? 1.5, 0. So there's my x-intercept, and then my y-intercept is 0, negative 3. 1, 2, 3. It's right there. What do I do to those 2 points? Just connect them like that. And then connect it like this. There we go. All right, very good. So we've graphed them both. Okay, that's what it meant by doing it graphically. So what are we concerned about? What are we looking for now? Where they intersect each other. And where do they intersect? Right there. And where is that point, do you think? Yeah, it's pretty close to right on. I'll tell you what, let's just do this, just so we can see it a little bit better. See where they intersect? Again, you got to be careful. It looks like a little tiny bit below there, but I'm pretty sure that's where it's supposed to be, right there. Would you agree? It should be. But sometimes, though, that's the problem with solving these graphically. If they don't intersect right on one of those intersection points, then it's going to be hard because then you're going to be guessing. Is it halfway? Is it a third of the way? Is it 0.32? Who knows, right? You'll be semi-close, all right? So this is not the most accurate way to do it, but it is a way, and people use graphing all the time, and they'll actually find out where those intersections of those lines occur, and it will tell them a lot of good information and all that kind of stuff. So what is our answer then? What are we going to write as our answer? We'll write it as an ordered pair because it's an intersection, right? It's a point. You know how we haven't done it yet this year, but when we do these things, even when you do them by substitution and elimination, we always write the answer as ordered pair. A lot of people might write x equals, y equals, but it's better to write it as an ordered pair because what does that represent? Why do we write it as an ordered pair? Because we're finding a point. That's right. We're finding a point, okay, that is shared by both of those lines, and that is it. So what is that point then? 2, 1, right? What if you didn't trust the graph, okay? What if you weren't sure? What if it was maybe you drew it slightly underneath of it and you weren't sure if it's supposed to be right on there or not. What could you always do? You could always check algebraically, couldn't you? Yeah, let's plug it in. All right, so I'm going to... All right, so here we go. Ready? So what was our answer? 2, 1? Let's just check. Now, I'm not going to make you do this, but I think it's a good idea to do it, though. All right, I'm not going to make you do it on a quiz or a test. But if you want to make sure that you're right, or at least have a better chance at being right on this, then I would check it. All right, so again, our answer is 2, 1, correct? So let's take that first equation, that first one right there. So what are we going to put in for it? 2 plus what? 2 times 1. And that should equal what? 4. Let's see if it does. 2 plus 2 is 4. Does that equal 4? Yep. So it works on that one. My guess is it's probably going to work on the other one. But let's just double check, make sure. So it's 2 times what? 2 minus 1. Let's see what that is. 4 minus 1 is 3. Does 3 equal 3? Yes, it does. It checks. So we're good to go. So you should be pretty confident, right, that your points actually work. Make sense? All right, let's do one more like this. We'll go a little quicker. And we're going to still solve it graphically, but we're going to do it by slope-intercept form this time. All right? And you could have done this by slope-intercept form if you wanted to. I'm not going to make you do it by y-intercept or x-intercept and y-intercept. So you can do it any way you want. But you got to do it by graphing, all right? And I have to see your graph, and it's got to make sense, all right? So don't just graph something crazy and then do it algebraically. Solve for x and y algebraically, all right? I got to see where they intersect. That's going to be part of getting the answer right. I have to see that they intersect in the spot where you said it was going to intersect. Make sense? All right, let's do another one. Example 2. I got 2x plus y equals 0. And then I got 3x plus 2y equals 2. All right. So what I'm going to do on this, I'm going to put them in a slope-intercept form. And again, this is probably your first instinct. Would you agree? To graph. So on this one, I can do this super easy. What's that? Y equals, get the 2x on the other side, negative 2x. All right, so I could graph that. We'll do that in a second. Everybody see what I did? Just subtract the 2x from both sides. 0 minus 2x, negative 2x. Let's do this one. So what am I going to do here? I'm going to move the 3x to the other side. So that gives me minus 3x plus 2, because that's already over there. Divide both sides by 2. All right, so what do I get? Y equals negative 3 halves x plus what? 1. So I'm going to graph both of those things. All right, so again, we'll do them in a different color. Let's do the first one. What's the y-intercept for that first one? It's 0. So put a little dot right there. And the slope is negative 2, right? Negative 2 over positive 1. And if I wanted to, just to make sure my graph is a little more accurate, I'm going to go down 2 over 1. I'm going to do that a couple times. You okay with that? I like to do that. And then we'll go up 2 to the left 1, up 2 to the left 1. I like to do that a few times just to make sure my line is where I want it to be. Because if you only have 2 points, and especially if they're really close to each other, your line can be off a little bit, right? It looks like it goes through those points, but maybe it doesn't quite. So that looks pretty good right there. Let's extend that down a little bit more like that. All right. And let's do this one. What's this one? Y-intercept is 1 right there. And then the slope is negative 3 over 2. So I'm going to go down 3, 1, 2, 3. I'm going to go to the right 2, 1, 2. Now this one's super skinny. I mean, it looks very close to this. Because what? That's negative 3.5 slope, or negative 1.5 slope. This is negative 2 slope. So the slopes are really close, aren't they? All right? So I'm really going to make sure that I do my slopes right. So it's negative 3, 1, 2, 3, 1, 2. And then let's do this. Let's go 1, 2, 3, 1. Oh, look at that. See, just by counting, I can see that intersection. You see what I'm doing? I'm going to go 1, 2, 3, and then to the left, look at that. Hits right on there. So I know right now where my line's going to intersect, don't I? All right, it's going to be right at that point. But let's just finish this up. Let's just draw this thing just so we see how similar the slopes are to both of those. Yeah. But again, what was I concerned about? This thing right here, that point. So where is that point? It's what? Negative 2, 1, 2, 3, 4, negative 4. So negative 2, positive 4, I should say. Positive 4. So that should be my answer. But what if I wasn't really sure about it? What could I always do? Check it, all right? Let's just put it in the first one right here. So it's going to be 2 times negative 2 plus what? 4. What's that? Negative 4 plus 4, that equals 0. And it's supposed to equal 0. So yes, that checks. Let's put it in for the second one. 3 times x. 3 times negative 2 plus 2 times what? 4. Let's see what that is. That's negative 6 plus 8, which is 2. And it should equal 2. And it works for both of them. So I'm good to go. I'm pretty confident. I'm like 100% confident that that's my correct answer. The checking's a good idea, especially when you're graphing. All right, when you're graphing it, sometimes, especially if you don't have graph paper and you're just doing this, watch. You're going, isn't this what a lot of you guys do? Right? You go like this, you go like this, and you go boom, 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 boom. And then you're not super careful. Yes? All right? Yeah. But if all I did was ask you to graph a line, right, and you put the y-intercept there and then a slope, it's pretty good. It's accurate enough. But if you're trying to find out where the point of intersection is, you got to be really, really precise with your lines. So I would not do this. Now, I always, it's way over there and I'm hooked up to the mic, but I always have a ruler with me, all right? And if I was going to do this, even if I was going to teach this stuff, now I didn't on this one because I was in the teacher's room. I didn't have a ruler. I'm like, oh crap. I thought about coming back and getting it. But if I want to make sure it's really accurate, I'm going to take a ruler and I'm going to mark off each little spot, right, exactly the same, up and down and left and right, okay? So do that. Or the best thing to do, obviously, is get what? Get graph paper, absolutely, okay? I've had people just do their whole homework on graph paper. I've had people just cut out the graph that they did on graph paper and like tape it to the paper. I've had students do that. It's fine. Don't mind that, all right? But I would use graph paper if I were you, all right? It just makes it a lot more accurate. All right, I'm skipping example 3. It's not because it's not important. It's actually probably one of the most important things on here, but just trying to get this done in a certain amount of time. All right, so what we're going to do now is not really solved by graphing. We're going to talk about 3 different types of graphs that you could encounter, okay? 3 types. If I give you a system of equations with 2 equations, you're going to encounter one of these 3 situations. Right now, we just had one situation, but there's 2 situations that you could get. The first one, I don't know why they use the word consistent every time. I would just be good with just independent and dependent. They put independent consistent. I don't know. I didn't read enough. I just looked at the title of this. I'm not sure if they gave an explanation of why they say that, but I would just say independent. The consistent part, I think I understand, especially for the third one, why they say consistent, but I would just say independent. So that means that our answer is only going to have one solution. So the two examples that we've done so far, how many solutions did we have for each of them? We just had one. We had one answer, didn't we? Okay, we had one ordered pair, one place where those lines intersect each other. All right? So that means that the slopes could not equal each other. If you looked at the slopes for both of those, both slopes were different. Okay, they had different y-intercepts, but you could even have the same y-intercept. All right? But as long as the slopes are different, okay, they're not equal to each other, we say that it's independent. So it would look like this. If you just had two lines that intersect each other, that would be considered an independent solution, okay, or an independent system. I'd probably be the best way to say it. Okay, it's independent. Everybody got it? So your normal lines, they intersect each other at one point. They got one solution, okay, different slopes. Then that's called independent. All right, the other one is dependent. Now, again, they throw the word consistent in there. I'm just going to say dependent. Is that all right? So I'm just going to say dependent. All right, on this one, you have an infinite number of solutions. Like, how in the world could I write infinite number of solutions? You have an infinite solutions. Okay? Now, here's a situation where the slopes are going to be equal to each other. So the slope of one line is going to equal the slope of the other line. But there's also something else that's going to be true, that the y-intercepts are going to equal each other. Now think about it. If I had two lines and both the slopes were the same and both y-intercepts were the same, tell me something about the two lines. They're the same line. They're the same exact line. Everybody hear me on that? All right, so that's what you have. So you got an infinite number of solutions because, check this out. There's a line, right? And let's make another line, copy, paste. Let's change the color of it. Now check this out. If I take this line right here, the red one, and I put it right on top of the white one, look at it. Do you see how many places do they intersect each other? At all of them. That's a good way to say it. I like that. At all of them. And there's an infinite number of places where they hit each other. Would you agree? That's why there's an infinite number of solutions. All right? So if they're the same line, all right, it's called dependent. All right, let's do one more. And the other one is called inconsistent. That's why they put the consistent. Dependent consistent, independent consistent. This one is inconsistent. That's correct. All right, so this one just has one solution. This has an infinite number of solutions, and this one has no solutions. So what kind of lines do you think you would encounter that never intersect each other? Parallel lines. Very good. All right, so what do we know about parallel lines? They have the same what? The same slope. But they're going to have a different what? Y-intercept. See what I did? I put B1, B for y-intercept. All right, they don't equal each other. All right, so when you have a situation like that, you're exactly right. You would have, whoops, I'll just leave it like that. Let's not. Let's make it look a little bit better than that. There we go. Copy, paste. There you go. There's two lines right there. And if they never intersect each other, and if they have the same slope and different y-intercepts, they will never intersect each other. And they would be parallel lines. All right, and I'll just write right here. Parallel lines are inconsistent solutions, okay? Because there's no solution. There's no way that they're going to intersect each other, and so there's no way that they share the same x and y. All right, that's an inconsistent solution. So what they're going to do is they are going to give you a system of equations, and they're going to ask you, are they independent? Are they dependent? Are they inconsistent? All right, that's what they're going to ask you. And you have to do a little work. You can't just guess. You don't just want to take a 1 in 3, chance to get it right. You want to make sure you know what you're doing. So what are we going to do? We're going to take them, look at their slopes, look at their y-intercepts, and basically this is what it boils down to. If what I'm going to do is I'm going to put them all into slope-intercept form. Everybody with me? So I'm going to take each of these equations that they give us, put it in slope-intercept form, then compare them. If they don't have the same slope, all right, then it would be independent, all right? If they do have the same slope and they have the same y-intercept, in fact, if they're both exactly the same equations, then it would be what? A dependent solution, all right? And if you look at them, you put them in y equals mx plus b form, and they both have the same slopes, but they have different y-intercepts, then you would say it's inconsistent. We got it? All right, let's do one. So they give you 3x minus y equals negative 1, and 2x plus 3y equals negative 8. Now, just looking at them right now, you may not be able to tell which one's which. But what do we want to do with them? Put them in what? Slope-intercept form. Okay, let's put them in slope-intercept form. So let's solve for y is basically what we're doing right here. So let's do this one. Can we do this in our head? Yeah. Add a y to both sides, subtract the 1. So what's y? 3x minus 1. Everybody see that? I just moved that to the right, move the 1 to the left. There you go. You got to do an extra step with this one, but let's get y by itself. So subtract a 2x from both sides and divide both sides by 3. All right, and so what's our equation here? Y equals what? Negative 2/3 x minus 8/3. It's kind of ugly slope. That's okay, because what are we doing? We're just comparing. Are these two completely independent equations? Yeah, they don't share the same slope. They don't share the same, and we don't even care if they share the same y-intercept or not. It's the slopes. They're different slopes. So what would I call this out of the 3 choices? Look in your notes. It's independent, right? And I'm okay if you just use the word independent. Okay? That's an E, not an A. Independent. Okay? So that would be the answer right there. How did you know the answer? Well, you did this, okay? You put them both into slope-intercept form, and then you looked at them, then you made a decision, yes, it's independent. If I graphed them both, they would be 2 completely different graphs. They would intersect each other, so there's one solution, okay? And I don't even care what the solution is. They don't even ask you for the solution. They just want you to understand, is it independent, dependent, or inconsistent? Everybody good with that? Yeah. I don't know why I keep asking that question all the time, because nobody ever says, nope, I'm not okay with that. Yeah, but see, I do it just to keep going on. It makes me feel good that, oh yeah, everybody's understanding because nobody says anything. But I know I've said it a million times. Everybody okay with that? And then I just keep going. And I know there's people out there that are like, I'm not okay with that. All right, so what are we going to do here? Solve for y on both of these. Agreed? Everybody look up here. We're going to solve for y on both of these. So we're doing the same exact thing. It's just when we get to the end, when I put them both in the slope-intercept form, then we just have to make a decision, right? And look at them, compare them, and that kind of thing. So let's see. Subtract a 9x from both sides. So negative 3y equals negative 9x minus 6, right? Divide both sides by negative 3. Negative 3. And I'll stretch it out here. So that canceled. So what do I get? Y equals 3x, what? Plus 2. All right. Now I do the other one. Get y by itself. Subtract a 6x again. So negative 2y equals negative 6x plus 4. Divide both sides by negative 2. All right. That gives me y equals what? 3x minus 2. What do we got? I got the same slope, but they're 2 different lines, aren't they? Because this has a y-intercept at positive 2. This has a y-intercept at negative 2. So this would be inconsistent. Exactly right. So you compare the two, and you would say it's inconsistent. Tell me something that these lines do or are. They're parallel to each other. That's right. These lines are parallel. Okay, one's above, right? One crosses the 2 at the y-axis, one crosses the -2. But they got the same slope, means they're parallel, so they're called inconsistent. Nah, let's use the words that they use, because they actually give it to you in the problem. They actually say, tell me if it's independent, dependent, or inconsistent. Now again, they throw that word consistent in there for the first two, right? They say independent, consistent, dependent, consistent. I don't need that consistent in there. Just put independent, dependent, or inconsistent. Last one, and we're finished. Excuse me. Talking too much today, I guess. All right, let's do one more. Every day I do. That's right. Tell you, when I first start teaching after being off for the summer, my throat is so sore after that first week of teaching. But then you kind of get used to it. But it definitely... Now I almost messed this up. When I was writing this problem on my own notes, what do you think I wrote first? Instead of 4y, I put what? 4x, yeah. But I looked at it, and I was like, ooh, that's a y. It's not an x. So you got to be careful with that kind of stuff. All right, so let's do it. Same thing. There shouldn't be anything new. So 6y equals negative 3x plus 9, divide by 6, divide by 6. So y equals, what's that? Negative 1/2. X, what? Plus 3 over 2, right? Just divided both top and bottom by 3. All right, let's do this one. Again, the y is first this time, so I'm going to go what? 4y equals negative 2x plus 6. Divide both sides by 4. Check this out. Y equals what? Negative 1/2 x plus 2 goes into both of those, 3 over 2. Check it out. They're both exactly the same, aren't they? They got the same slope, and they got the same y-intercept. So what do we call those? We call them dependent. Dependent. Oh, dt. Did I spell that right? Dependent. Yes. Okay, so it's dependent. So that's your answer for that. That was your answer for the other one. That's pretty easy to see, right? You just got to know what words match up with what. But anytime you have a system of equations, can you think of any other situation that we could have? I can't think of anything else. Can you? No, because there's not. All right. They either intersect each other at one point, they intersect each other at every single point, okay, or they don't intersect each other at all. That's the only choices you have. All right. And they got words for all of those. All right. I got through that pretty quick. Guess Victoria's not used to our boring class, so she knocked her out pretty quick. Okay, so that's all right. You're a visitor. You can sleep if you want. Section 3.1. I gave you the lesson plan already, but I'll write it down just so I have one more place where you can check. 9 to 23, that would be a lot to do, wouldn't it? So I just gave you the odds. Okay? So just do the odds, don't do them all. And what can you do since I gave you all the odds? After you do a problem, what should you do? Yeah, you should check your answers. Now, you should not be doing what? Just flipping to the back right away and then writing down the answer, because you got a lot of work to show. There's no way you can just give me inconsistent, dependent, or in this situation, just say, oh, my solution is negative 2, 4. And then you just write negative 2, 4 down and don't write anything else. There's no way in the world I'm going to accept that. All right? Again, I don't check homeworks on right or wrong, but you got to show me. You got to show me the graph specifically, all right? Because this is about graphing. So you have to show me the graph. Even before you graph, there's work to do, isn't there? Right? You got to put it in slope-intercept form. Tell you what, after you do this assignment, you should have that slope-intercept form and graphing down pat. I mean, you should have it already, but after this one, definitely you should have it down pat. Everybody good? All right. That's all I got.